Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. We are in the process of learning how cryptocurrencies mimic the properties of fiat money. In this lesson and the next few lessons, the property we are focused on is how Bitcoin accounts are secured. We will learn about the three numbers a Bitcoin account holder is assigned when acquiring a new account, namely, the private key, public key, and the Bitcoin address. We will then learn about the functions performed by these three numbers, as well as a high-level overview of the mathematics behind their derivation. We will conclude with reflections on the role of mathematics in enforcing Bitcoin account security. We are currently learning the method by which cryptocurrencies mimic the second of the four properties of fiat money, namely account security. In this lesson and the next, we will cover how these accounts are secured, similar to how passwords and PINs secure bank accounts. In the previous lesson we learnt that Bitcoin payments are authenticated via digital signatures. However, to understand digital signatures, we need to do a little more groundwork. Hence, in this lesson, we will go back to the three numbers we encountered earlier in this course. X was derived by picking a random number between 1 and a very large number. Y was derived by applying a formula to X. Z was derived by applying a formula to Y. Z, we said, is the blockchain address, which is equivalent to a bank account number. Y is called the public key. X is called the private key. When we open a bank account, we get a bank account number. When we wish to get a Bitcoin address, we get three numbers: the private key, the public key, and finally, the Bitcoin address. We can call these account numbers the Bitcoin account triad. The mathematical logic behind the generation of the Bitcoin triad is such that the probability that the same private key, public key, and Bitcoin address can be generated twice is close to zero. From a data perspective, we can visualize the following table that presents a generalized framework across all crypto tokens. Each row in the table is a unique blockchain address, which is associated with a specific blockchain network like the Bitcoin blockchain or the Ethereum blockchain. Associated with each blockchain address is a unique private key and public key. Each row in this table is unique. Even beyond that, each address, public key and private key is individually unique. The value stored in a Bitcoin address can only be transferred with knowledge of the private key. The private key is thus equivalent to online banking password or a PIN. We have learnt that the private key is equivalent to a password or PIN of a bank account. The Bitcoin address is equivalent to a bank account number. So, what is the public key? Next, we will learn the intuition behind the public key. Imagine you are the proud owner of the email address jamesbond@gmail.com. You wish to prove to a friend who lived overseas that you own the mail ID. There are two ways to prove that you own this coveted mail ID. One way is to share the password of the email ID with your friend. He could then test it himself by logging in. But of course, you are not likely to use this method. The second method, which most people would choose, is to send emails from the ID jamesbond@gmail.com. You can tell your friend that you are sending an email from that address and the email would have the words "Happy Birthday." Your friend gets the email and is now convinced that you have access to that email address. In this example, we can distinguish between two types of information. The first is information that grants access to an account. In this case, it is the password. The second is information that proves access to an account. In this case, it is the receipt of an anticipated email. The private key is equivalent to the password. The public key helps in proving that you knew the private key in the same way the anticipated email does. The mechanism by which the public key accomplishes this purpose will be covered in the next lesson. We can now summarize the functions of the Bitcoin account triad. The private key grants access to send payments from a Bitcoin address. It is equivalent to an online banking password. The public key is used to prove knowledge of the private key to the world, without actually revealing the private key. The Bitcoin address is equivalent to a bank account number and allows the user to hold the value of cryptocurrency. At this point you may be curious to see how public key, private keys and Bitcoin addresses look like. Next, we will generate these keys online to get a feel for them. Instead of relying on a bank to assign us an account number, in Bitcoin, we generate the address ourselves. Let us go to the site called bitaddress.org. I will keep wriggling my mouse till a Bitcoin address is generated. The wriggling of the mouse is a trigger for the software to generate the Bitcoin address. Otherwise, it wouldn't know when to start doing its thing. Now that the Bitcoin address is generated, we can see the associated private key. Since everyone can see the private key on this video, I will not use this blockchain address to store any Bitcoins I hold. Next, we click on link called Wallet Details. I now copy and paste the private key. We can now see the Bitcoin address, the associated public key and private keys. The private key, public key and Bitcoin address are all numbers, though they are displayed using an alphanumeric representation system. The goal of the demonstration we just covered was to make the Bitcoin account triad real. However, you may be curious as to what people actually do to get a Bitcoin address and start transacting. Most of us have an idea of what opening a bank account looks like, either in branch or digitally. What is the equivalent of the bank account opening process in Bitcoin? We will cover this later in the course. Here are some takeaways on the Bitcoin account triad. The private key, public key and Bitcoin address are all large numbers, which are represented in alphanumeric forms. Knowledge of private key is required to transfer the value stored in a blockchain address. Private key is secret. The public key is known publicly because third parties use it to verify whether someone knows the private key. The Bitcoin address is known publicly because it acts as the destination to which payments can be sent. One notable feature about the Bitcoin triad is that they are mathematically related. This is very different from traditional banking. The password of your online banking account is not mathematically related to your bank account number. Why do we not have all this math in the world of fiat money authentication? In the world of fiat money, the bank systems validate whether the password or PIN we entered matched what was expected. The expected values are kept in the bank systems. Similarly, a bank is able to validate a wet signature on a check because it has the specimen signature on its records. All this is not a problem, unless, of course, someone hacks into the bank system. But in cryptocurrency ecosystem design, authentication must occur without anyone, except the account holder, knowing the private key. This is feasible through mathematical functions, whose application requires a mathematical relationship within the account triad. Now, let us carefully look at these two statements. First, the private key is secret but the public key and Bitcoin address must be public. Second, the public key and the Bitcoin address are mathematically derived from the private key. Next, we will see why these two statements, on the surface, create a contradiction. Consider a set of simple mathematical equations. The private key is x. The public key, y, is 5x. The Bitcoin address, z, is 2y. In the crypto ecosystem, all mathematical functions being applied are publicly known. The problem is that if you make y or z public, anyone can back calculate the private key since the formulae are known to everyone. Even if we used much more complex mathematical equations than this example, one could deploy computers and back calculate the private key. To solve the problem we just discussed, mathematical functions used in the derivation of the Bitcoin account triad exhibit three properties. First, they should yield unique input-output pairs. The second property is asymmetry. The third property is non-guessability. Next, we will look at each one. The property of a unique input-output pair means that for a given output, you could only have one input and vice versa. Consider the equation where x squared is equal to 25. X is the input. 25 is the output. The mathematical function used is the squaring of a number. There are two possible values of x, +5 and -5. Hence, this is an example of an equation where the property of unique input-output pairs is not present. We can introduce two terms here. First is determinism. This means that the mathematical function will yield only one output for a given input. Second is collision resistance. This means that for one output, the mathematical function can have only one input. The property of unique input-output pairs means that both determinism and collision resistance exist. Consider another example. The output is 100. The input is x. The mathematical function is the multiplication of the input with 5. In this example, there can only be one value of x, which would fit the function. However, the problem, of course, is that such an equation can be back calculated. Hence, a second property, namely, asymmetry, comes into play. An asymmetric mathematical function means that you could apply a formula to convert x to y and y to z in such a way that it is not possible to calculate backwards. Next, we will see a simple example of this. Consider the function where we raise the number 100 to the power 0. The answer is 1. Now I tell you the output, which is 1. I also tell you the mathematical transformation function, which is raising a number to the power of 0. Next, I ask you to determine what the input, x, was. You will not be able to answer my question since any number raised to the power of 0 is 1. This is an asymmetric function. You cannot revert to the original input by calculating backwards. The problem, of course, is that while this function meets the criteria of asymmetry, this does not yield unique input-output pairs. We want an asymmetric function because we don't want someone to calculate the private key. But what if they could randomly guess it? The third characteristic of this desired mathematical function is that the probability you could guess the correct input by random chance is close to zero, even when you know both the output and the mathematical function that resulted in the output. It would be like winning a lottery with trillions and trillions of lottery tickets out there. We can now assess the functions that we just reviewed against the three criteria we just discussed. Consider the x to the power 0 function. It does not meet the first criteria because for a given output, 1, there are multiple possible inputs. It is asymmetric because you can calculate it forward but you cannot figure out x backwards. Since any number to the power 0 is 1, there are infinite number of possible x's. Hence, it is impossible to guess which number was used in the forward transformation. Hence, this function meets only 2 of the 3 criteria. Consider the function x squared equals y. The input could be a positive or negative number. Hence, it does not meet the first criteria. We cannot calculate the input backwards with certainty since there are 2 possible options. Hence, this function meets the second criteria. It is asymmetric. Finally, since there are only 2 possible inputs for a given output, the input is guessable. If the output was 25, there are 2 possible inputs. The next function is 5x equals y. It meets the first criteria. However, it is symmetric because if you knew the output and the mathematical function, you can determine what x is. Finally, if for some reason, you didn't want to calculate x despite knowing the mathematical function applied, you could guess the input. If the output was 1000, you could punch into a software program every number beginning 1 till the program found a match with the correct x. The input is very guessable. We can infer from this chart that it is not easy to find a mathematical function that meets all 3 criteria. At this point, you may be wondering what type of mathematical transformation meets all the 3 criteria that we discussed. The conversion of private key to public key occurs via something called elliptic curve multiplication. The conversion of public key to Bitcoin address occurs via what is called a hash function. While the mathematics behind this is beyond the scope of our course, it is useful to understand the intuition behind these functions. Next, let us look at these functions briefly. An elliptic curve is simply a family of xy graphs that follow a specific type of equation. Bitcoin uses a subcategory of such elliptic curves. Without delving into the mathematical intricacies, what occurs, at a high level, is that there is a point on the curve that is universally known and is called the generator point. This generator point is the same for everyone. It is like a train station from which every train departs. When an individual requests a Bitcoin address, a random number is generated completely outside this graph, by a software program. Let us call this number small k. This is the private key. Depending on the value of this random number, a certain point is chosen on the elliptic curve. The x-coordinate of that point is the public key. Let us call this number capital K. The distance between the x-coordinate of the generator point and the x-coordinate of the public key is dependent on the value of the private key. There is only one public key corresponding to a private key and vice versa. The underlying mathematical logic is such that it computationally infeasible to either calculate or guess small k from big K. Hence, no one can derive the private key from the public key by either computation or guesswork. This is the property of asymmetry we discussed in the previous lesson. While the conversion of private key to public key occurs via elliptic curve multiplication, the conversion of the public key to a Bitcoin address happens via a hash function. A hash function takes an input of any type and converts it into a fixed length output. We will go to this website where I will type in passwords of various lengths. The output is always fixed 32 character long. Hash functions display the same 3 desired properties of asymmetry, fixed input-output pairs and unguessability. There are many types of hash algorithms. The one that we just saw is called MD5. For the conversion of public key to the Bitcoin address, Bitcoin uses a couple of hashing algorithms. These have complex names like Secure Hash Algorithm and the Race Integrity Primitives Evaluation Message Digest. In this course, we don't need to understand their inner workings. The resulting number is represented in base 58 format. We learnt in a previous lesson that base 58 is an alternative to the decimal system of representing numbers that we are more familiar with. Once again, for the purpose of this course, we don't need to get into the mathematics. The takeaway here is that the benefit of hashing the public key is to have Bitcoin addresses of a more compressed length. It is important to note that the mathematical functions used in Bitcoin and the numbers generated from them are by themselves purpose neutral. The outputs generated are like any other number. However, the Bitcoin system is using these numbers to perform a certain function. For instance, a private key is just a large random number, just like your email password is a sequence of alphabets, numbers and characters. Hence, as end users who are learning about the crypto ecosystem, while it is useful to have a base understanding of how these numbers are derived, our main concern is with the purposes to which the numbers are deployed. It is easy to get lost in the math. Hence, let us summarize the benefit of the mathematical properties used in the creation of the Bitcoin account triad. First, the property of unique input-output pairs ensures that one Bitcoin address and public key cannot have multiple private keys associated with it. Second, the property of asymmetry allows the public key and Bitcoin address to be public while keeping the private key secret. Third, the inputs are unguessable from the output. You cannot derive the private key by bringing even the most advanced computers to guess the input. Once again, the benefit of this is that the public key and Bitcoin address can be public while the private key remains secret. Let us summarize the takeaways from this lesson. First, when acquiring a Bitcoin address, the user gets issued 3 large numbers. We can call them the Bitcoin triad. These are private key, public key and Bitcoin address. Second, the 3 numbers are mathematically related. Third, the properties of mathematical functions used in generating the Bitcoin triad ensure that the private key can remain secret, even though the public key and Bitcoin address derived from it are public. Fourth, the private key is equivalent to a password and the Bitcoin address is equivalent to a bank account number. Fifth, the public key enables an independent validator to test whether the account holder knows the private key, without the latter sharing the private key with the validator. We just summarized what we learned. But it is also useful to summarize the questions that have still not been addressed. First, how does the public key help test the knowledge of private key? We will cover this in the next lesson on digital signatures. Second, we said that when acquiring a Bitcoin address, a user gets issued the Bitcoin account triad. But we haven't covered the actual workflow by which this happens. We will cover this in a subsequent lesson. This brings us to the end of this lesson. Review the summing up section of this lesson before proceeding to the next one.